Hey guys, the coronavirus has not yet got Mr. Longbrake, so I'm here with you doing notes on combined gas law. Be on page 21 in your guys' packets, and we'll go ahead and get started. So first we're going to cover the formula for combined gas law, and the formula we'll write down here is P1 times V1 all over T1 equals P2 times V2 all over T2. P stands for pressure, V stands for volume, T stands for temperature. This is a little bit different formula than what we're used to. The four previous gas laws all had two variables, but as you can see here, this gas law has three. And it's actually a combination of Boyle's, Charles, and Gay-Lussac's laws, which we've already covered, hence the name combined gas law. Another big thing to remember about this is that there are two sets of conditions. And that will be very important when comparing this to the ideal gas law, which we're going to cover when you guys get back from spring break. But the ideal gas law only has one set of conditions. So that's how you really tell the difference of when to use the combined gas law versus the ideal gas law. Another thing to remember is that the temperature, just like with our other gas laws, has to be in Kelvin. And the way we get Kelvin is we add 273 to our degrees Celsius. So that's the basic formula for the combined gas law. Now let's do a couple of practice problems. So practice problem number 1 is pretty straightforward. I'm going to go ahead and circle the initial conditions in blue. It says a gas balloon has a volume of 106.0 liters when the temperature is 45.0 degrees Celsius and the pressure is 740.0 millimeters of mercury. Then it says what will be its new volume, so that is a second set of conditions, at 20.0 degrees Celsius and 780.0 millimeters of mercury. And then I'm going to go ahead and label those variables on the left side of the page, just like we've been doing. So I have a V1 of 106.0 liters. I have a T1 of 45.0 degrees Celsius, and I'm going to go ahead and add 273 to that and convert it to Kelvin right away because I need to do that before plugging it into the formula. When I do that, I'm going to get 318.0 Kelvin, making sure that I keep the place value of my original temperature, which is in the tenths place. So I did that. And then I have an initial pressure as well. That initial pressure is 740.0 millimeters of mercury. And then I'll go ahead and do it for the final set of conditions. V2, well, it's actually what it's asking for, so I'm going to leave that as a question mark. T2 is 20.0 degrees Celsius, which I'll once again go ahead and add 273 to. And when I do that, I get 293.0 Kelvin. Once again, keeping the place value. And then P2 is going to be 780.0 millimeters of mercury. So now I have my variables labeled, and I am ready to plug them into our formula. So our formula is P1, which is 740.0, times V1, which is 106.0, all over T1, which I converted to Kelvin, 318.0, equals P2, 780.0, times V2, which is what I'm solving for. So I'm going to leave that as V2. If you would like to go ahead and substitute X in for that, that's totally fine as well. All over T2, which is 293.0. So I have my numbers plugged into the combined gas law. Now I'm ready to go ahead and solve. And the way I do this, two ways. I can cross multiply and divide, which many students choose to do, or I can go ahead and simplify and solve algebraically. So I'm going to go ahead and do that method. And what I'm going to do is I'm going to take this whole left side and simplify it into one number. And that's because there's no variables there. So I can go ahead and do 740 times 106, and then take that number and divide it by 318. And when I do that, I get 246.67. I'm not going to round until the very end. Equals 780.0 times V2 all over 293.0. Okay, Next, I'm going to go ahead and get 293 out of the denominator. And the way I do that is I'm going to multiply both sides by that denominator. And when I do that, I'm going to get on the left side 246.67 times 293.0 will give me 72,273.33 equals 780.0 times V2. And now the last step to get V2 by itself is to divide both sides by that 780. And so when I do 72,273.33 divided by 780, I'm going to get a V2 to be equal to, rounded to 4 significant figures. And the way I know 4 sig figs is because if I look at every single number in my problem, each of those has 4 sig figs. So the least number of sig figs is in fact 4. And so V2 rounded to 4 sig figs is going to be 92.66 liters. And that would be my final answer. So that's a more straightforward problem, and there are other problems just like that on page 21 that you can follow along with and look at my answer key. But I'm going to go ahead and move to a more complex problem. And this problem says if the initial volume, and I'll once again circle those in blue, of hydrogen gas is 10.0 milliliters at a pressure of 75.6 atmospheres and 60.0 degrees Celsius, what is its new volume at STP? Well, if you look at this problem, it's very different because it seems as if there's only one set of conditions. And I'll go ahead and label those. V1, 10.0 milliliters. And it's okay that it's milliliters. It does not need to be liters in this particular formula. I have a P1, which is 75.6 atmospheres. And then a T1, which is 60.0 degrees Celsius. Well, I have those initial conditions, but the issue here is I don't have a second set of conditions, or at least it doesn't seem like that. But if you look at this fancy word here, or abbreviation, I should say, STP, we've actually covered that abbreviation earlier in the unit. That stands for standard temperature and pressure. And so if I scroll over here and look at this graphic here, this is the same graphic that you can see on the back of your periodic tables. And when I look at this graphic, I see STP right here, and it says standard temperature is 0 degrees Celsius, which is 273 Kelvin. And standard pressure, there are 4 different values for each of the different units of pressure. And so basically all you have to do is match the unit of pressure to the unit of pressure that is in your problem, and you will have standard pressure. So if I look back at the problem, my initial pressure is in atmospheres. Therefore, I need to make sure that the standard pressure is also in atmospheres, and that value is 1. So I'm going to scroll back over here, and I actually do have a second set of conditions. And I'll label those. V2 is what I'm solving for. P2, standard pressure, we just looked on the back of the periodic table, is 1 atmosphere. That's standard pressure in atmospheres. And T2 is 273 Kelvin. And those are exact numbers, so those do not factor into our significant figures when we solve our final answer. But one thing I do want to make sure I do is add 273 here to get our initial temperature in Kelvin. And when I do that, I get 333.0 Kelvin, making sure I still go to the tens place there because my initial temperature goes to the tens place. Now I'm ready to go ahead and plug these in, and it becomes just like the last problem we solved. So P1, 75.6 times V1, 10.0 milliliters, all over T1, 333.0 Kelvin, equals P2, which is 1, times V2, all over T2. And that's where our STP comes into play. Now, once again, I'm going to simplify this left side of the equation. And when I do that, I am going to get 2.27. So 2.27 equals 1 times V2 all over 273. Next, I'm going to get 273 out of the denominator, and the way I do that is by multiplying both sides by 273. So I'm going to do 2.27 times 273, and I'm going to get 619.78 equals 1 times V2. And then lastly, to get V2 by itself, I'm going to divide both sides by 1. Well, anything divided by 1 is just itself, so V2 is going to equal 619.78. And last thing to do is to round to the proper sig figs. I look at my initial numbers, 3 sig figs, 3 sig figs, 4, and then these do not count for sig figs because they're exact numbers. So the least number of sig figs is 3. So when I round this to 3 sig figs, this is tough. The 7 makes the 9 round up, and that makes it 620. But if I leave it like that, it only has 2 significant figures. So I either need to put a line over that or put a decimal. And then my unit here is milliliters because my initial volume was in milliliters. So that was a more complex problem, pretty much one of the more complex problems that you'll ever see with combined gas laws. So if you feel comfortable with that, you should feel really ready to go. If you have any questions, please do not hesitate to reach out. I hope you all are doing well. I miss you guys, and I'll talk to you soon.